Hello and welcome to this video. Today we gonna look into the secure hardware architecture concept, but this gonna be a two-parter. So this is the part one and we will follow up with part two in the next session. What we're gonna look in part one is the aged concept of the CPU, which is still very well used in today's modern computing. Uh, how does the CPU functions and how does it becomes, sorry, important part of the hardware architecture which on which the computing is based. So the basics of the hardware architecture or basics of any hardware that we use in the computing is the system unit, is what we call as a system unit. Then underneath that unit, we have different components. For example, a motherboard, a central processing unit, the CPU. There are memory slots. There are firmware where the actual code resides for the hardware to operate, and there are PCI slots for the connectors. Then there is also peripherals, as you may know, that we require a keyboard and mouse as an interface, as an input interface to interact with the system. Uh, as you have seen in the different layers of operating system, uh, the kernel, which is at the core of it, is something that an end user cannot directly access. The same stands for the hardware, that we do not directly interact with the hardware, but we do it through interfaces uh, for which mouse and keyboard are just the simple examples. Then within the hardware system, there are other communication architecture that connects different components and help to communicate with each other. They are called the computer bus or the system bus architectures, and they act as a channel for various input and output devices to help in communication. Uh, there is this concept of north and south bridge, but this is more dated, which is used basically to help understand the system architecture, but that is something commercially you will not hear too much about it. So it's a very core engineering kind of conversation that you may heard this term of north bridge and the south bridge. And what they do again is that they connect things. There are no standard protocols of how they connect, so they tend to, how do you say, work with each other without a standard protocol. But the design is in such a way that the design itself sets the protocol for them to communicate with each other. What is important in to understand in system hardware architecture is the various concepts that we have previously seen as well in the operating system context, and that is multi-threading, processing, tasking, and what kind of a programming has been done to make sure that the instructions are translated into something what the machine can understand. And these are all happens in a different uh, group of memories. That's why you will have different kind of memories operating in an hardware. You have virtual memory, the physical memory where the actual bits and byte calculation happen. There is also external memory, the disk or the hard disk, which gets connected to fetch in data and give data back for hardware to work upon. Since we have such a critical system attributed to hardware protection, isolation mechanism, how do we provide hardware segmentation so that the data in one sector do not overlap with the data or instruction in another sector, all those becomes very widely used and very widely known categories for which you have to be very clear about. Now, In terms of external memories, there are different kind of configuration. For example, you can have a warm media, which is like write once and read many times, and it is basically used for the resilient application for data retention, where you would want data to be retrieved, but not getting tampered by the retriever. Also, that you want to save the data in such a way that the backups are not manipulated. So that is where the warm disk comes into picture. Central processing unit, as we said, is the core, is the brain, so to say, as many attribute of an hardware system. And what it is built of is uh, is different kind of processors with different clocking speeds. It has an ALU, the arithmetic logic unit, which helps it in the calculation. And it also has a control unit, which is like fetching the data to and from the memories for which it has to act upon. Now, the data could be simply data, or it could also be part of instruction that the CPU requires to perform its function. How does it work? There is an attributed or designed cycle of how the instructions and data interact in this aspect in the CPU. So there is a procedural step of you fetching, decoding, executing, storing, and then pipelining the output to where it's supposed to go. Now, in most of the cases, unless or until you are dealing with the hardware configuration directly, you may not have to deal with this cycle or have to know about this cycle. However, for academic purposes, it is good to know that also within the hardware, which we don't see often with the naked eyes, the calculation has a programmable logic on which it is based, and that's why it is important to have some understanding about it. So then they also work, as you must have seen in other high-level programming languages, that it also has an interrupt instruction, what you called, for example, exception in a high-level programming languages. It also has inbuilt processes or multi-threading process. That is something you also encounter in high-level programming. And there are also threading, which are lightweight processes which are meant to only perform one single task. So for example, if a thread only has to open a communication port between two channels, a lightweight thread is just that simple implementation where it only opens port between two channels, and it has no other functionality attributed to it, and it cannot do anything else. So they are lightweight in nature, that they are just functioning for a single instruction or a given set of tasks, or only one task among given set of tasks. So this is in a nutshell how you should understand the CPU, which is core to the hardware architecture that we dominantly used. Of course, there are higher level configurations of GPUs and now even TPUs, which performs this calculation at much higher scale, at much higher speed, but the underlying concept more or less remains the same. So with that, I'll stop. Thank you very much for listening, and I'll see you in the next session where we will carry forward on this hardware architecture security to part 2. Thank you very much.